guys, this is our hurricane video makeup lecture on section 6.5 arc length. Couple comments before I get started and jump into things. Some of you guys may have noticed 6.5, this is a little bit of a skip forward for us. Now, reason for that is I figured I'd try to pick a lighter lecture and move stuff up for you guys. So you weren't learning something quite so heavy as 6.3 independently on your own. You don't need section 6.3 or 6.4 to do this section, so don't worry about that. We're just going to skip around a little bit so y'all get the lighter stuff first. Comment number 2 that I wanted to point out before I jump into things. If you are not a person that likes video lectures, there is a PDF available of this lecture on my Moodle page. Go to the course notes section. Everything's grouped by test. In the test 1 folder, there should be an arc length lecture somewhere. Okay, so if you'd much rather prefer to read than to listen, you are welcome to do that. Comment number 3 that I should make, regardless of whether you look at the PDF or if you watch the video, do be aware there is a quiz associated with this lecture, so make sure that you skip over to the end of the video if you want to make sure that you catch that problem. Okay? Now, without further ado, I'll go ahead and get started. 6.5 on arc length, what is this section? What's the point of this section? Well, a lot of the stuff that we're doing in this unit is using integrals to solve problems. The section's no different. We're just using integrals to compute lengths of curves. Now, if you're wondering why integrals, well, there's this theme in a lot of the sections in this chapter. Geometric formulas only take us but so far, right? We have area formulas for things like squares and circles, but not general area under curves. We have volume formulas for things like cones and boxes and spheres, but not general solids of rotation or general solids. Similar deal here, we only have a distance formula for straight lines, but not for general curve length. Now, to really highlight what I'm talking about, I can draw you guys a picture here of the setup that I'm describing. If I have some sort of interval that I care about and a curve on that interval, well, if this is a straight line, yeah, this is something that we actually have a nice formula for, versus, maybe a case like this where I have a general curve on the interval from A to B. Now, who knows why I want the length of that curve? Maybe I'm manufacturing some sort of object out of wire. I need to figure out how long it is. Maybe I'm building a road. I want to figure out what kind of length that guy has. We have generic formulas for segments, but not straight lines. Now, if you're worried about the generic formula for a segment, you could use the distance formula where you mark out what your beginning x and end x values are, as well as your beginning y and end y values. If you imagine figuring out your difference in x values and your difference in y values, and if you pretend I can draw a straight line, this guy looks like a right triangle. Your distance formula basically abuses Pythagorean theorem to figure out what this length is. Now, on the other hand, there's no triangles here on the right hand side, so we can't pull the same trick. So we're going to use an integral formula, but I'll switch over to the next slide here. Usually I don't like telling you guys that things work because I said so, so we are going to discuss the idea behind why the integral formula works. Okay, so we're going to build this integral formula. Again, my disclaimer, if you are a person that just wants to know the formula and how to use it, you're welcome to skip ahead a little bit. But if you're one of the people that you like knowing why it works, or it'll help you understand it a little bit better, here we go. What I'm going to do to get my integral formula is start with an approximation. right? We don't know how to do general curves, but we do know how to do straight lines. So if this guy was a collection of straight lines instead, well, that would be much easier to deal with. So I am going to pretend that that's the case, right? We'll look at a collection of straight lines that roughly approximates our curve, okay? So we will go ahead and use line segments as my approximation. And then once you have those line segments, we actually do know how to use a distance formula, or you could if we refreshed whenever you guys saw that first. You could use a distance formula to figure out each of those individual lengths. So go ahead and sum your distances. Okay, so what would happen in this picture is piece number 1 plus piece number 2 plus piece number 3 plus piece number 4. Add all that up, all those lengths. We'll take that as an approximation for our curve. Now I know that this is an approximation because our curve is bendy and longer in some places than the straight line segments that actually approximate it. But again, we're starting with an approximation. So for the moment, we'll deal with that as being okay enough. Now, let's break this down for an individual line segment. Okay, I'll scroll down a little bit. For individual line segments, what am I doing, right? Well, again, the idea is if you can break down the distance in x values here, so I'm going to call this guy delta x for my change in x from my beginning left endpoint to right endpoint. If I broke down my distance in x values and my distance in y values, it would almost be like I'm building something that looks like a right triangle, and then I could go ahead and use Pythagorean theorem to solve for that side that I've marked with a question mark, right? So here, if I want a length, okay, I will give a little approximation here. We want my square root of delta x quantity squared plus delta y quantity squared. Now this is actual length of this segment as I've marked, but again, these line segments are approximations for the bits on the curve that we were initially looking at. This is why I'm dealing with the little squiggle in the middle here, okay? So again, the whole idea of where this is coming about is, we're using Pythagorean theorem to generate this. If you squared both sides of this equation that I've given you guys, it looks a lot like a squared plus b squared is c squared, okay? Now, this expression, this root x squared plus y squared business, for sake of our approximation, for sake of the fact that we are eventually going to cram this into something that looks like an integral formula, it's not the tidiest format for me to write this in, so I'm going to do some manipulation of this expression. All right, I'll scroll down just a little bit more and note that we need to manipulate this expression to make it more suitable for shoving into an integral later. Okay, now some of these steps might look a little counterintuitive. They aren't really simplifying. They'll probably make the expression look a little bit more complicated, but they will ultimately help us with shoving stuff into the formula. Okay, the first step that I'm going to do to twist this thing around is this delta y squared term. I am going to multiply this by delta x squared over delta x squared. Okay, inside the radical. Comment number 1, that doesn't change anything because it really looks like I multiplied by 1. Really fancy but stupid version of 1, but it looks like I multiplied by 1. Comment number 2, this is going to help us so that everything that we're writing down looks like it's written in terms of x, so that later, if we build an integral, we can integrate with respect to x, and we won't have x's and y's jumbled in. Okay? Next thing that I'm going to do, I will go ahead and pull out a delta x squared, because now there's a delta x squared on both of these terms. If I do that, I've got a delta y squared over delta x squared term here. Another thing that I can go ahead and do, and I'll do these two steps at once. First off, you'll notice that I'm square rooting this delta x squared. If you root a square, technically I should get absolute value of x, or in other words, the root and the square should cancel in a way. Delta x was referring to a positive distance though, so I'm just going to let that cancellation happen. Okay, my root and my square, but the square root's still going to be on everything else in the parentheses. So here it's still on that 1 plus this fraction. The fraction I'm going to rewrite a little bit. This looks like delta y divided by delta x, but then like I squared it. Okay? So other comments, I'll give myself a little bit more room here to work with on what I'm doing. I will make a little side note that this delta y over delta x that I have, that I'm squaring in this expression, usually you guys see change in y over change in x a lot. This really looks like the slope of whatever that line is, okay, that we were trying to find a length of. Slope, on the other hand, is usually something that you could use a derivative to compute. So instead of the slope of that curve, I can think about the derivative of that curve if it's a segment. It's really the same thing. So rather than using delta y over delta x for whatever function expresses that segment, well, I could go ahead and just use f prime of x, okay, or y prime of x, either way. Okay, so I'm going to go ahead and make that substitution in this expression here. Okay, I will write this delta x root 1 plus my f prime function squared, and recall that this is going to give me my approximate length of my segment if I have a function to describe the segment. Now, the catch here is that this is just an individual segment, right? If I scrolled up, this was just me manipulating that square root of delta x squared plus delta y squared. Okay, this expression here, what was that? We just said that that was length of this individual segment, and that individual segment was an approximation for this overall curve. So this expression that we've cleaned up, this is just one piece in a whole. So if I wanted to sum my whole curve, okay, if I want my whole curve length, this guy should be pretty close to what happens when I sum up all of these. Now I'm going to go ahead and kind of shift my order a little bit of these pieces. I'm just going to throw my delta x on the end instead of out front. I'm using a little bit sloppy notation here because I should be, indexing each of my terms and telling you how many pieces I'm summing. But at any rate, the idea is that this expression looks like a Riemann sum, right? So this expression, if you actually did formally index each of the terms and count up how many segments you're adding and number and label everything, this is going to be a Riemann sum for the actual length. So if you took a proper limit, refined this so that you're taking more and more segments to get a better and better approximation, that's how you get the actual integral formula, which, I'll kick this over to the next slide here. This guy, arc length, actual arc length, is given by this integral, right? You'll notice on the last slide we had root 1 plus f prime squared was the bit that we were summing. I'll go ahead and flick back really fast so we can see that. Okay, root 1 plus f prime squared okay, times delta x, that's what we're summing. When you take the limit, you get this integral back. So at this point, this is no longer an approximation. This will give us true length, okay? We've taken the limit of our Riemann sum to get this integral. Now, if you didn't care about the derivation, you just want to know how the formula works, this is where we kick back in. If you haven't noticed, I have boxed this section. This is our key takeaway for today, is how to find arc length of curves. You will need to know what interval your curve lives on. You will need to know the function that is used to express your curve and how to take a derivative of it. But aside from that, this is a very direct formula to use, okay? There's no real crazy decoder here. The interval that they give you, and you will be given an interval, is what you use for your bounds. The function that they give you is what you're taking derivative of and plugging in here, right? So I'll give you all a couple tips for usage of this. Even though the setup is a lot more straightforward than our volume sections, we're going to run into slightly different problems. We're trading easier setup for harder integrals, okay? That's why you guys get tips with this section, okay? First thing that I will start off with, and this maybe comes across as really silly, but don't forget to derive and square. Please, please, please don't forget to do that. Like I said, it's maybe a somewhat silly looking tip because most of the formula, or the important part, is, hey, there's f prime and we're squaring it. It's actually a really common mistake that I see a lot, that people will just shove the f function in here and add 1 to it and forget that they have to do stuff to f. Okay, so don't forget to derive and square. If you mess up either of those steps, you're integrating the wrong thing, you're going to get the wrong length back, and actually you're probably going to set up a really nasty integral that you can't do. Okay, so don't forget to derive and square. Brush up on those derivative rules, because little things like chain rule and stuff like that, they'll mess you up. Okay, so make sure you've got your derivative straight and your algebra straight to square this. Other tips that I should mention, usually what is going to happen with a lot of these is that they're going to turn into either one of two things, either simplify problems or U-sub problems, right? You'll notice I've got a derivative, I've got to square it, I've got to add stuff to it and take it. These are going to look messy outright. So granted, a lot of the problems you guys get are going to be kind of contrived so that they're actually doable. With that said, though, they're contrived, so you have to do some algebra to clean this up and actually take an integral. Another reason why U-sub maybe might be a good thing to consider is that we're setting up an integral that's already got compositions built into it. So probably going to run into one of those techniques. The last tip that I am going to give you, and this is a very, very, very important one, so actually I am going to star this multiple times. When you go to take a square root of a sum, maybe I'll give you a generic sum here. This guy is not going to be the same thing as if you root each of the pieces. Now, okay, fair, maybe there's a couple special cases in which this works, like if A is 0 and B is 0 in this example, sure, that's a special case, but in general, this root pattern almost never works out, okay? Reason being, roots are effectively fractional powers. This root is about the same thing as if you take a half power. The rules of exponentiation do not let you split exponents across sums in this manner. So you can kind of think about it this way. For a very similar reason, for the fact that a plus b quantity squared is not a squared plus b squared, you have to FOIL instead. Very, very similar reason. We cannot split apart roots in the same manner. So it's a super common mistake for people to just look at this formula and say, oh, this is the same thing as 1 plus f prime. No, do not do that, okay? So the reason that the second tip was to simplify or do U-sub It's primarily that we can't simplify in this manner, so we have to find some sort of way to address that root. And you cannot address the root by splitting it up this way. Okay, we can never do that. So, without further ado, let's take all that information and actually see if we can apply this formula to some examples. Okay, first example, length of y equals 2x plus 5 on 0, 1. I specify using calculus because this is a straight line, so technically you could get away with using distance formula or drawing out a diagram and using Pythagorean theorem, but I don't want to do that. I want to actually see I'll use this formula. So the first thing I'm going to do is just write out my formula so I remember what I'm working with. I'm not doing anything fancy yet. I'm just copying the formula down. Okay? Now, you notice if I'm taking f prime and squaring it, I need to know what f is to get f prime in the first place. So I'm going to start there. What do I use for f? Use whatever function you're actually trying to, find a length of the curve for, right? So we were given y equals 2x plus 5. Y is a simplified way to say f, or f of x is a fancy way to say y in this case if we're talking about a curve. So I'm just going to use 2x plus 5. If that is my function, my derivative falls out pretty quickly. We just get 2 because the constant term drops off. And now I have stuff that I can plug into my integral formula. Now, for my bounds, you will pretty much always be given an interval. We said 0 and 1 bound x, so I'm going to go ahead and use those. Don't think too hard about it. You're given an interval. Use it as your bounds. For the rest of this, I need to plug in my derivative and square it. Well, my derivative is 2. I need to square it. This is my integral that I get to take to compute length. Now, I obviously don't want to leave it as is. I can clean up what's inside of the radical here. At this point, I can antiderive. Let me scroll down to give myself more room. When you go to antiderive this, please don't try to write it out like 5 to the 1/2 and then do power rule or what. No, 5 is a number. You square root it. You get another number. This just means that we get to slap an x on this thing and call that our antiderivative, right? Root 5 is a number, so it'll antiderive just like 2 or 10 or 15 or whatever. At this point, I can evaluate my bounds. That means plugging in my top and subtracting what happens when I plug in my bottom bound. Multiplying anything by 0 gives you 0. And multiplying anything by 1 gives you itself. So in this particular case, root 5 was our length. Okay? This is how we would use calculus to solve this problem. If I want to try another example, let me see if I can click over here. I'll give you a different curve. You can find the length of the unit semicircle on -1 to 1. Again, using calculus, so that means I will start with my formula, right? You guys will need to know the formula to be able to tackle any of these problems. So I'll start with my formula. What do I need for that? I need to know what function I'm working with and what derivative it has. So again, for the function, pick the curve you want the length of. Okay, the curve is y equals root 1 minus x squared. So I'm going to use root 1 minus x squared. Now, I do have to take a derivative of this. This is why I mentioned we should really be up on our derivatives. If I want to put this in a slightly easier format to derive, I can remember that roots are half powers, so this is the same thing as 1 minus x squared raised to the 1/2. This is power rule and chain rule together for me to take a derivative. If I take a derivative of something to the 1/2, I should get 1/2 something to the minus 1/2. Okay, power rule to get the coefficient and exponent here, and then chain rule says we copy over the inside verbatim. Chain rule also says we multiply by the derivative of the inside, and my derivative of my inside is going to be 0 minus 2x. So I get a minus 2x here. This is a gross expression for me to try to plug back into my arc length formula, so I don't want to leave it as this. I probably want to clean it up a little bit first. Some comments on things I can do. First off, I have a minus 2 and then I have a 1/2. The minus sign isn't going to go away, but the 2 and the 1/2 will cancel each other out. If I want to clean this up, I can go ahead and note that that minus x is not really going to go anywhere, but everything else is to a negative power, so I can flip that into the denominator. If I have a half power in the denominator, I'm really taking a square root. So this is how we clean up that expression and write it a little bit more compactly. Okay? Now, that is my derivative that goes into my integral formula. I said just use whatever bounds they give you, and substitute in the derivative that we found. Do not forget to square that derivative. Okay, and this is what we're going to be integrating. Okay, this will give us my length of that semicircle. Now, if I scroll down and give myself a little bit more room, obviously we sure don't want to integrate it when it looks like this. This is a hot mess. So let's see what simplifying will let us do. Okay, couple things that I can do to simplify. First off, I can actually square that fraction that they gave me. Okay, so if I square the numerator, the negative sign is going to drop out. I'll just get x squared. If I square the denominator, square over square root, that'll cancel. I'll get 1 minus x squared. At this point, I've got a fraction that I'm adding to something else. I probably want to try to actually add those two objects together, but it doesn't currently have a common denominator. So I'm going to make 1 have a common denominator. I can express 1 as 1 minus x squared divided by itself. This will give me the common denominator that I need to actually force these two objects together and take their sum. Okay, and at this point, if I go to actually add these, when you add fractions, you usually go straight across the top. That means that this 1 minus x squared is going to be added to x squared, and in that case, the minus x squared and x squared are going to cancel. I will get root 1 over 1 minus x squared. Now, a comment about this, and I will scroll down and give myself a little bit more room. This is actually a basic rule. It maybe doesn't look like a basic rule right now immediately, but it is. Reason being, if I take the square root across both the numerator and denominator in my fraction, root 1 is itself. Root 1 minus x squared, I'm going to leave as is. And if you're up on your antiderivative rules, you should recognize that this is going to be my arc sine function. Okay. Now, if I go to evaluate my bounds here, we always plug in the top number first and then subtract off my bottom number second, evaluated in my antiderivative. And at this point, while this is technically an answer that gives you length of the curve that we asked for, I expect you guys know unit circle values for trig functions. And even though we don't work with the arc trig functions quite as much, the idea is basically this. If I want sine inverse of a number, I am asking you guys, what angle did I take sine of? And it gave me this number back, right? So what angle do you take sine of? And it gives you 1. Well, you take sine of pi over 2, and it gives you 1. And over here, I'm asking what angle do I take sine of, and it gives me minus 1. A note about the range of the sine inverse function, pretty much everything that this spits out is going to be between minus pi over 2 and pi over 2, so never give anything in the second or third quadrant. Another thing I should note is if you're in quadrant 4, use the negative values. The angle that you take sine of to get minus 1, in that case, is minus pi over 2. My signs are going to cancel, so then I'm adding. I'm just going to get pi back. Okay? And again, if I call back to what I was initially finding a length of in the first place, I will scroll up really quickly to demonstrate. This is the length of the unit semicircle on minus 1, 1. Okay, if I wanted to draw that guy out, you know, unit semicircle on minus 1, 1, well, this guy has a radius of 1. If I know my general, circumference formula, I want half of the circumference of a radius 1 circle. So instead of 2 pi r for full circumference, I want half of that, which is pi r. In this case, my radius is 1. So pi times my radius gives me the pi that we just came up with. So granted, in this particular case, this was a geometric object, okay, right here. This guy's a semicircle. But, if you were wondering how that circumference formula came about in the first place, or, why the circumference formula, why we trust it to work, this arc length formula is one of the ways that we can prove that it actually gives you a legitimate number. Okay, the arc length formula or the circumference formula for a circle didn't just come out of nowhere. Now, I've given you guys 2 examples, where we can get away with geometric things to find length. I started out with a straight line, and then I gave you guys a semicircle. Sure, we don't really need the formula for those. We kind of need the formula for this one, right? This is actually not a geometric object. This is something there's really no workaround for. We need this formula. So I didn't even specify use calculus because this is our only way to get arc length here. If I want to find the length of this curve, again, much like my previous examples, I'm going to start out with figuring out my function, figuring out my derivative. So I will hang on to my constant coefficient and then apply power rule. I will also clean some stuff up so that I have a little bit nicer of a derivative to plug in. If I use the appropriate interval and if I substitute stuff in, well, this will be 2 root x that I am squaring here for my example. Now I'll scroll down and give myself a little bit more room. This is something we can clean up a bit before we try attacking it. Namely, I can actually square my derivative. Don't forget to square both pieces here. And at this point, we can't simplify much more, right? I've already told you guys that if you have a root of a sum, you cannot split it apart into each of the pieces rooted. So what I'm going to do instead, since this is a composition, is just try u sub, right? Usually we do the inside function for my u, and then its derivative for my du. You'll notice that there's no leftover 4's, so I will have to correct this coefficient here. At this point, when I go to substitute everything in to this integral, well, I'll worry about the bounds in a moment. I'm no longer taking root 1 plus 4x. I am taking root u. I no longer have a dx on the end. I have a 1/4 du. And for my bounds, okay, you could do the thing where you work with this and then go back to x later. I like fixing my bounds. If we wanted to fix my bounds, we have to take these bounds and substitute them into the u that we chose, right? So if I substitute 0 into my u function, 1 plus 0 gives me 1. And if I want to substitute 6 into my u function, 1 plus 4 times 6, that's 1 plus 24, that gives me 25. Okay, so ultimately, if I want to simplify this, Another way to think about this is I'm anti-deriving a half power. That's what roots are. So I could hang on to my coefficient and then apply power rule. That means I'll have added 1 to my exponent and then divided by the same number. If you want to clean this up a little bit, dividing by a fraction that is really the same thing as multiplying by the reciprocal. And this is something that I can still stand to clean up a little bit. Namely, that fraction, if you cancel out the 2 and the 4, you're left with a 2 in the bottom. It's being multiplied by 3, so your coefficient's 1/6. If you don't like the fractional powers, if you have no clue what the heck to do with them, well, remember that fractional powers are going to give you roots. The denominator tells us that we have a square root. The numerator, that just acts like a normal power. Okay? So to evaluate this, I'm going to have to plug in my top number. Okay, so I'll root 25 and then cube it. And then I have to subtract what happens when I plug in my bottom number, meaning I have to root 1 and then cube it. If I'm cleaning this up, you know, my square root of 25 is the same thing as 5. If I cube that, it's 125. Basically, it means I have a fraction 125 over 6 here. Over here, if I'm rooting 1, I get 1. If I'm cubing it, I get 1. So I'm really subtracting off a 1/6 here. The rest of this should be some fundamental algebra for us. I subtract across the top. And if you don't like the fact that both of those are even, okay, we'll get this guy as my length of my curve. Okay? I'll try one more example here, and this is actually going to be kind of a crazy one, okay? These are going to be kind of hard. I mentioned before, these are usually U substitution or simplifying problems. This is going to push some of your algebra to the limits, I think, with simplifying, okay? So an example like this. I want to find the length of that curve on 0, 2. I will pretty much always start out with my integral formula and figuring out whatever my function is. So in this case, the curve that they gave me, this is my function. Now, when you're taking your derivative, please don't forget about chain rule. Not much is going on with this first term, but this second guy, when you derive the exponential function, you have to multiply by the derivative of the inside, which is -1. That means I'm actually going to subtract off this second term, okay? So now when all of this goes into my integral, I've got my bounds that they gave me, but this thing that I'm squaring is actually going to be kind of large and messy here. Okay, so this e to the x minus e to the negative x over 2, that's what I'm squaring. Now, some comments here. I've usually started by actually taking that square. For me to do this on this step, I'm going to FOIL, okay? I will actually FOIL out those terms. Now, if I FOIL this out, I will note that it is a square. There are some shortcuts for taking squares. Namely, and I'll do this in a slightly different color here. If I'm looking at just this piece, well, if I do my square formula, it'll save me a little bit of writing. My square formula says that you get to square the first bit. This is e to the x over 2 squared. Take 2 and multiply it by both of your terms. So actually, this shouldn't be a plus sign here. Let me go back and erase this guy. this should be a minus sign because, 2 times a times b, okay, 2 times my first term times my second term. My second term was negative, that's why I just shifted that to a negative sign. And I get to square my last term. This is e to the minus x over 2 squared. Now, some comments on simplification here. First off, if you have a power raised to a power, you multiply. So this is really e to the 2x on this first piece. I'm squaring the bottom, so this will be over 4. For my middle term, I will make a cancellation here so that I'm not dealing with that extra 2 as a coefficient, but this will be a negative term. Another comment is if I'm multiplying two things that have the same base, okay, e to the x and e to the minus x, you add those exponents. So if I take e to the x and e to the negative x, well, I'll go ahead and write that out. On my next line of simplification, that'll really be e to the 0, and that's just 1. So my next line of simplification, those are going to cancel each other out. Similar comment over here, if I take a power to a power, I multiply, and I can't forget to square the bottom. And this means, ultimately, I'm going to get e to the 2x over 4 minus a half plus e to the minus 2x over 4. Okay? So, all of that algebra, this is something that's going to go back into this slot from my integral. Okay? I just did that as scratch work. So my integral at this point should look like this guy. My bounds have not changed. The fact that all of this is in a root has not changed. This 1 has not changed, but I actually did FOIL stuff out to get this expression. Okay? Now, this is not the end of me simplifying, because I can go ahead and make a note that these terms, okay, my minus 1/2 and my 1, they're both constant terms. I could actually combine those guys if I wanted to. So I'm going to go ahead and do that, and I'm going to do kind of a strange thing with the position that I write these in. I'm going to not leave the constant term in the front. I'm going to leave the constant term in the middle. Okay, so this e to the 2x over 4, that will lead. If you take 1 minus a half, it gives you plus a half. And this term on the end did not change. This guy is still over 4, and that's what I'm integrating. Okay, now here's the reason that I wanted to highlight this. If I scroll down just a little bit, I want you guys to pay attention to this sort of triplet of terms here. Okay, so I'll point this guy out, along with the triplet of terms that I have inside of my radical here. You notice the only thing that looks different between both of these is that one of these has a minus 1/2 and one of these has a plus 1/2. Now, a comment, both of these are squares. And what I mean by that is this. If I scroll back up to figure out where this, upper triplet of terms came from, it came from me taking this e to the x over 2 minus e to the negative x over 2 sum, or difference, and then squaring. Now, here, kind of a way to think about this is that this little triplet here, it really kind of looked like some sort of a minus b quantity squared. This was why my middle term comes out negative. It just turns out that, a, what I'm treating as a here is this e to the x over 2, and what I'm treating as b here is this e to the minus x over 2. you notice that if you take a minus b and you square it, and you compare that to what happens when you take something like, let's say, a plus b and you square it, the only thing that's different between both of those two formulas is that if you expand these out, the middle term in the first one has a negative sign and the middle term in the second one has a positive sign. That's the only thing that's different between both of these expressions. So what that's going to tell me is this. If I know how this guy factors, that means that I really know how this guy factors. What this is going to look like, if I factor it, is this upper expression here, okay, that I'm trying to point out with my cursor, looks like this upper expression, except for the only difference is that it should have a plus sign in the middle, right? So what I'm trying to hint at is we want to use my earlier work to help us factor this thing, okay? What that earlier work suggests is that when I do go to factor this thing, it is indeed a square. It'll look like e to the x over 2 with an e to the minus x over 2, except for the difference is that instead of subtracting like we did before, we're now adding those terms. Okay, so if I scroll back up real quick, this looks exactly like this guy, except for I've just got, let me point that out again, this guy, except for it's got a plus sign in the middle. Okay, that's what our algebra suggests. So if I pull that factorization trick, I'm now rooting a square. This means that I can take a cancellation, so it looks like e to the x over 2 plus e to the negative x over 2. And at this point, I can use some of my basic rules to antiderive. Okay, I'll get e to the x over 2 minus e to the minus x over 2 if I treat this as a kx problem. At this point, I can go ahead and evaluate. Get e squared over 2 minus e to the negative 2 over 2. Now we'll subtract off what happens when I plug in 0. This will be e to the 0 over 2 minus e to the 0 over 2. That will obviously cancel out. Okay, so this bit here is our ultimate answer. Okay, if you don't like the format of that, if you don't like negative exponents, you are also welcome to present it in this manner. Okay, I have some comments for you guys. I'll give you guys a couple notes on this. I know that was a weird sort of algebraic simplification problem. This isn't the only case that you're going to run into that sort of a trick or technique, but it is probably one of the harder of these kinds of problems that you'll see. If you end up running into problems where you're summing something that looks like 1 over x to the n and x to the n, and it needs to be squared, you get a similar factorization trick. Okay, so that same thing where you maybe start out with a minus b squared and you need to later write it as a plus b squared, you're probably going to do a similar factoring trick. So be on the lookout for that. Another note that I'll go ahead and make is that, I've done all of these guys as y equals f of x problems. This is kind of a minor point of concern. It'll look ever so slightly different, but the work is the same. If you have x equals f of y problems, you basically use the same formula. I'll point this out in an example. If I give you x equals f of y, kind of like this, on a y interval instead, well, formula really doesn't change much. We're still integrating from a to b. You're still taking a square root of 1 plus a derivative. Here it's just f prime of y instead, okay, and you're integrating with respect to y. So the only thing that's really going to be super different is we're working with y, right? So if this guy is my function, I still need to be able to take a derivative In this case, I'll need chain rule, so do be careful about that. I still get to plug this in, okay? So I'm still given an interval. Okay, I said above it went from 0 to cube root of pi. I still have to plug in my derivative. Right, this is 3y squared cosine y cubed. I still have to square that derivative. Okay, just make sure that your stuff is written in terms of y's. Now for the sake of this problem, this one's a little bit too messy for us to actually try to handle. This is why I asked you to not solve it, but do note the formula works about the same. I will leave you guys with a final note, okay, before we jump to this quiz that I promised. Again, I have said before, root a plus b is not root a plus root b. This is why we're doing U sub. This is why we're doing those crazy simplifications. This is why I was really testing y'all on algebra on those last couple examples. We cannot break this down in this manner. So I'm going to write with big old capital letters here, do not ever, 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 ever simplify like this, right? I really want to emphasize this because this is a super, super common mistake and probably the most common mistake that I see made on problems like this. The reason that they're hard or that they look hard is because we're doing U sub to avoid this mistake. We're doing simplification to avoid this mistake. The fact that we cannot simplify this way is what makes these problems hard, algebra wise. Okay, so don't make this mistake. Okay, that out of the way, here is the quiz that I promised. Figured I'd at least go light on y'all. If you need a refresher, this looks like the first example that we tackled, right? Use calculus to find the length of this line on this interval. Again, just send this off to me whenever you guys get back from the hurricane. Alternatively, I do take quizzes late, so if you want to ask questions to me about it before you turn it in, or get a chance to get help on campus before you turn it in, turning late is fine. If you run into fast questions, I can also take stuff by email. So, in general, if you have questions on this lecture or anything related to the problems, please feel free to come see me when we're back, or maybe shoot me an email for faster questions. I expect to see this quiz at some point from you guys whenever we're back in town. Till next time.